I'm thrilled to be here representing our Rocket Lab Mission to Venus team. Next slide, please. So I think why we're going to Venus is a number of these mysteries that have been talked about at this conference and for many decades in some cases. And so the questions that are driving us relate to, go back please, thank you, relate to what is the nature of the ultraviolet absorber, and can we better understand potential thermodynamic or chemical disequilibrium in the clouds? And what about those potentially non-spherical mode 3 particles? And what we know, we are also driven by the question of habitability and perhaps life by this temperate zone in the Venus clouds. And while it's very clear that this temperate zone is far too dry and far too acidic for life as we know it, that is not the limit of what we can explore. And so we want to ask the question, are the Venus clouds habitable for life as we don't know it? And if not, what are the limits of chemical complexity? Now, I think even in this room, there's probably a lot of variability on this question. And I come to the table in our group, I don't personally think that there's life on Venus, but if there is, I definitely would want to find it. And furthermore, I think it's always important to test the null hypothesis, and that will support all of the other astrobiology missions that are either underway or in conception. Next slide. So these are the main goals of the mission. And first and foremost, we have our science goals to better understand potential habitable conditions writ large in the Venus clouds. And Rocket Lab also has a number of goals related to maturing their interplanetary photon spacecraft, really pushing the limit of what can be done with small spacecraft, and also with a quick timeline. And we also are envisioning this as the first in a series of missions to better understand the Venus clouds, potentially culminating in a Venus sample return. That's something we're studying. We just wrapped up our NIAC phase 1 with that work. So the science objectives for this mission are search for the presence of organic material in the Venus clouds. And maybe you heard some hints from Jan earlier at this meeting about how we might do that. I'll get to that in a moment. And we also want to seek these anomalous cloud components, such as the potential aspherical mode 3 particles. Next slide. So this is our team. I'll highlight that I'm here representing today Sarah Seeger and our broader science and instrument team, Janusz Petkowski, also acting as the deputy PI for that group. Myself at Georgia Tech, Daryl Baumgardner at Droplet Measurement Technologies is developing the key instrument. We've got a number of other team members, many of whose names you might recognize, like David here in the room today, Jan as well, and Steve Benner and Maggie Tolberg at CU Boulder is doing a lot of the sulfuric acid aerosol work that's underway. And on the Rocket Lab side, we have Peter Beck, and we've worked most closely with Richard French and with Christoph Mandy. And so I'm thrilled that with Rocket Lab as a partner, we have not only a partner deeply interested in engineering and the technical side of the mission, but also in an intellectual interest in the science. Next slide. Oh, and I also want to say we've had a number of discussions with NASA, and so I'm grateful for NASA's support, particularly around entry and heat shield and DSN. So that's something that we're in discussion about. Okay, so why are these our objectives for the mission? Well, one of the key findings, historically, we might have imagined from our high school chemistry class that we couldn't really see much interesting chemistry happening in sulfuric acid. Our organic material might be destroyed. And yet, in the oil industry, there is some deep knowledge that when sulfuric acid is used in hydrocarbon processing, that there are residual organic materials that remain, so-called red oil that Jan mentioned earlier. And so here's a key experiment that Jan did with the Murchison, a fragment of Murchison meteorite, showing that There are residual components, organic materials that remain in sulfuric acid and that they are fluorescent. And so this forms the potential basis for seeking evidence of this organic material in the Venus clouds, looking for this fluorescence. Next slide, please. So Jan and Steve Benner made some measurements of a number of different simple organics and mapped out their peak excitation and emission spectra. And that's we saw this plot earlier during the meeting here. And so what we envisioned was, how can we detect this in situ? So the horizontal orange lines indicate laser emission frequencies that we consider emission wavelengths. And then the red line and the red band indicates what we ended up selecting as an excitation wavelength and a detection band to look for signs of these simple organics. Next slide. And could I ask anyone online to mute? Okay, so in addition, how could we address composition and sphericity? And so we're going to take advantage of Mies scattering, which is essentially Maxwell's equations applied to a particle in which the particle is similar or larger than the wavelength of light. And so in comparison to, say, Rayleigh scattering, where the scattering particle could be much smaller, with Mies scattering, there's an enhanced directionality. And we can take advantage of that with a detector to determine the size of the particles, and also by looking at deviation, by looking at polarization, we can also determine sphericity. So a spherical particle doesn't have a significant effect on polarization, whereas an aspherical particle does. So at our detection, we can add a polarization filter and look at both S and P components. Next slide. So putting this all together, we envision an instrument which has now been built called the autofluorescence nephelometer. And this is based on an earlier device that's been flown on commercial aircraft all over the planet. And so that's the setup being illustrated here. There's a vehicle skin, and above that you can see an airstream flowing by. That airstream, we have an emission laser to provide a source of coherent light. And then we're using our optics to interrogate a certain collection volume in that laser beam. And so we can detect single particles. And then there's a polarization detection module separating any scattered light into those two components. And finally, for this instrument, what we've done is we've added a fluorescence detection channel. And so Daryl Baumgardner at Droplet Measurement is the one who had developed this earlier backscatter cloud probe. I'll talk more about that in a moment. And this represents, we think, the perfect instrument to address our two objectives simultaneously. Next slide. Okay, so our mission timeline is as follows. We are planning to launch in January of 2025. And this will be on an Electron launch vehicle. And once we get to orbit, there'll be some phasing, very similar to the Capstone mission that went to the moon. And after about 7 days, we'll have our trans-Venus injection, and then about a 4-month cruise phase before we arrive at Venus. And when we're getting close to Venus, the probe will be released from the cruise stage about 30 minutes before entry. I'll have a coast phase, and then I'll talk more about the entry in a moment. Next slide. So this is what the Electron looks like. And I have to say, it's frankly amazing to me that we can go to Venus on a rocket that's only 1.2 meters wide and 18 meters high. It's unbelievable to me, but that's what's possible. And so this has some great heritage from Capstone, and also the same spacecraft bus, the high energy photon, is going to be used for the Escapade mission as well. And this platform has a delta V of more than 3 kilometers a second. And so that's what supports, in combination with Electron, this incredible capability. And now when we get close to Venus, our entry probe shown here is this sphere cone, a 45-degree angle sphere cone of about 40 centimeter spherical diameter. Next slide. And our instrument that's going to be inside that sphere cone, the AFN, we can trace the heritage all the way back to Pioneer Venus with the LCPS. And so that instrument worked in a very, also took advantage of me scattering. So this is a tried and true approach for spaceflight as well as here on Earth. And so the commercial product that's flown on aircraft all over the planet is the backscatter cloud probe there shown on the far left. It's about a 10 centimeter instrument. It has the scattering, and then a later version of this was developed that also added the depolarization feature to make the backscatter cloud probe with depolarization, or BCPD. And that's been evolved a bit further into the AFN with that fluorescence channel. And then, as you can see, the optics on the right have been designed so that we can look out about 20 centimeters, and that allows us to get into the free stream. So in summary, what we can get from this instrument is particle size, and then we can also use polarization to get an estimate of asphericity and complex refractive index that will, from populations of particles, that will tell us about composition and finally fluorescence. Next slide. So this is the way that the interior of the probe will look, and the AFN inside there looking out into the free stream. The CFD analysis has been done to allow us to have high confidence that by targeting out about 20 centimeters, we will be out of any influence of the heat shield. And that's something we definitely want to avoid, because the heat shield and sulfuric acid could interact and produce some confounding factors. Next slide. So once we launch and make our way to Venus, arriving in May 2025, we will have our entry phase. Next slide. And that's what this will look like. We have a few minutes during the entry phase until we will go subsonic, and it's at that point that we will initiate the measurement phase. And during that time, we will be going from 65 to 45 kilometers in about 5 to 6 minutes. So unlike some of the prior missions where we heard about years of measurement and many gigabits of data, we're talking hundreds of kilobits and 5 to 6 minutes of measurement. And we'll also be collecting temperature and pressure measurements. And our data rate is capped at about, we actually can transmit at several hundred bits a second, and we'll be collecting and reducing our AFN data down to about 1 kilobit per second, transmitting the most important data first, and then we will have a continued transmission phase for about another 10 plus minutes until we reach the design limit of the probe. Next slide. Thank you. So this is the current state of work. An initial prototype of the AFN was assembled and tested at Maggie Tolbert's lab at CU Boulder. And then the flight AFN is under final assembly and going to be going through environmental testing. And we're also working on the data analysis algorithms to do that real-time processing and summarization. And so that is where we really want to put a lot of effort into that optimization process to make sure we get the best science possible. And this is some of the testing that's underway. You can see on the right with the flight instrument and fitting into an approximate capsule size, and some of the aerosol testing that we'll be doing more of soon in the lab. Next slide. So we do intend to fully open source all the data. So we want to have our data end up in the PDS, and indeed we talked with NASA about that. There's certainly a precedent for PDS archiving of non-NASA missions. And so our intention is to release raw, calibrated and derived data products, noting that the raw data products will, in this case, be inherently summaries because we cannot send all the raw data back. But it is we're working on the optimal transmission strategies. And while we think we have a pretty good plan for that, I'd certainly invite any innovative ideas that you may have. Next slide. I'd just like to thank our partner Rocket Lab with this, and also Breakthrough Initiatives for early support and some design study work that led to the instrument identifying what were our objectives and what key instrument could fulfill that. Also to some unnamed MIT alumni for funding initial prototype development, and to NASA for their support related to heat shield and DSN, and Droplet for even contributing some funding early on to get some key work done on the instrument, and a number of other contributors. So we're very grateful for all of their support and also for your support. Many of you have acted as advisors, and we really appreciate it. Thank you so much. Next slide.